Yeah, we are in day 6 already, and today we're doing chemistry. We're going to be talking about the periodic table and some trends about the periodic table. Don't forget to get your notes and your pen right now so that you can take as much as you can. Now, the periodic table, what exactly is this thing about? The first thing we notice here is that there's something called periodic. And what does it mean for something to be periodic? Periodic simply means there's a form of repetition after a certain range of thing has been completed. For example, if you look at these our 50 days of tutelage, we had math the first day, then followed by physics, then followed by chemistry. And the moment we get to the fourth day, we switch back to math, then physics and chemistry again. So this is the sixth day now. So when we get to the seventh day, that will be tomorrow, we go to math again, physics, chemistry. So what is going on is that this thing is actually periodic in nature. Whenever we hit the third day, there's a kind of like reset. Things begin to look like they were before again. So math, physics, chemistry, math, physics, chemistry. The same thing is what happened in the periodic table as well. The only difference here is that we are dealing with elements. So as those elements go from left to right, as they increase in their atomic number, then when we reach a particular number, they reset again. So for example, when we go from hydrogen to helium, that's our first period anyways. So when we go from hydrogen to helium, that's the first period. You can see as the atomic number has increased. When we get to helium, we stop, then we go again to the second row, and that will be lithium, beryllium, then we go to neon. Then when we get to neon, it starts again. So for every period, we are always counting at least from the minimum of 2 elements to maximum of 18 elements. Minimum of 2 elements, maximum of 18 elements. And so altogether we have 7 periods. That's 1, 2, 3, 4, 5, 6, 7. So you can label them that this is period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Now, that is for the horizontal one. Now for the vertical place is where we have the groups, and they go like that from group 1, group 2, group 3, group 4, group 5, up till we get to group 18 here. Now, let me quickly talk about hydrogen. Hydrogen is a special guy. Fine, we sort of always place it in group 1, but the only major thing that it shares, like the property that it shares with group 1 is that it has one electron in its valence shell. I'm going to be explaining the concept of valence shell and then valence electrons very soon as well. That's like the only major thing that it shares with them. So technically, if we want to pick group 1 element, we should always start talking about lithium, sodium, potassium, and the likes. So take note of that. Now, this group 1 element is a name we call them. We call them the alkali metals. Group 2, starting from beryllium as it goes down, we call them the alkaline earth metals. And I'm going to skip the middle guy here for now. This middle guy, I'm going to skip them for now. So I'm going to go to group 13. Group 13 is what you would typically know as your group 3. This one, group 4, group 5, group 6, group 7, group 8, or which we also call group 0. But anyways, this is like a very old method of seeing the periodic table. These guys are actually group 13, 14. If you see some textbooks, they will say group 3A and all of those things. But you can just see them as group 13, group 14, 15, and so on like that. So I'm going to talk more about these later in this class. Quickly, I want to introduce you to the blocks that we have in the periodic table. Each of these elements are categorized into block. As you can see, obviously here, you already see the guys that belong to the F blocks. The F block, they are also rare earth elements. We have the lanthanides and the actinides. But we also have other blocks here. We have the S block. The first guy here, this group 1 and group 2 guys, they belong to the S block. This middle guy that I just circled now, we call them the transition metals. They are the D block element, the D block. So we have D block, we have the S block. And this guy at the right here, we have the P block element. We have the P block element. And also to my left, to the left, you have metals. But when you go to the right, especially to the P block side, you begin to have non-metals, from metalloids to non-metals actually. Now, what if you don't have the periodic table in front of you and you're given an element and the only thing you have is the atomic number? How can you determine the block that they belong to? What you need to do is to write their electronic configuration. And whatever subshell that they fall under, that the last electron that you feel fall under, that would be the block that they will belong to. So I'm going to pick random elements here, but before I do that, I quickly want to go to the off-box principle that we talked about earlier. I know I only gave you for 4 energy levels. I gave you from 1s. Then we entered 2s, 2p. We did 3s, 3p, 3d. Then we did 4s, 4p, 4d, and we did 4f. I didn't go to 5. I didn't go to energy level 5, energy level 6. And here's one thing I want you to notice. These energy levels actually correspond to the period as well. So from here, ignoring the lanthanite and actinide now, we have 7 of them, 7 energy levels. Now, if you want to write this, we can actually have 7 of them in this place. And if you remember what I told you is that for every energy level, you will always have the same number of subshell. If you're in energy level 4, you have 4 subshell. That implies that if I go to energy level 5, that will be, sorry, what am I writing for again? That will be 5p, 5d, 5f. We should have a 5g here actually, because it is energy level 5. And in fact, when we go to 6, 6s, 6p, 6d, 6f, 6g, we should have a 6h. And when we get to 7, 7s, 7p, 7d, 7f, 7g, 7h, we should have 7i. But the thing is that we kind of ignore some of these guys, and I'm going to strike them out very soon. So I'm going to use green for the ones that we're going to be using, and I'm going to use black to strike out the one we're not going to be needing. So I'm going to give you the reason why. If you look at general diagonal rule, or if you look at your textbook, some things are ignored. Now, if you go by the diagonal rule, you are going in this manner, you're going in this manner, you're going in this manner, you're going in this manner. Yeah, you go like this. Yeah, you go in this manner. Yeah, I think that makes sense. That makes sense. That makes sense. That makes sense. Yeah, and so on like that. Now, I think I should also add the 8s. 8s, 8 blah 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 blah, and there's this guy here. So this guy can easily cross down to this place. So let this guy just reach 8s like that. Now, there's one thing I want to show us here. I've given you the maximum number of electrons that can go in each of these places. And we have 103 of them. 103, like that's the maximum number of okay, here we actually have 118 here. So let's see. 118. If you want to distribute all of these things, how many electrons? So let's see when we exhaust all the number of electrons that we have as far as the periodic table that we have today. So 118 electrons. Let's distribute it quickly. That's going to be like a little bit long. Now, starting from, so I'm going to list it out. Let's go to 1s. From 1s, we go to 2s, 2p, 3s. This is actually a very tedious thing to do, so just try to follow along. We have 3s, we have 3p, we have 4s, we have 3d, 4p, 5s. I've explained all of these before, so just try to follow along. I've done 3d, 4p, 5s. So we now have 4d, then we have 5p, then we have 6s. Then this time now we have the 4f. 4f follows. Then we have 5d, we have 6p, we have 7s. Yes, 4f, 5d, 6p, 7s. The next diagonal will be 5f, followed by 6d, followed by 7p. 7p is the next, and followed by 8s right there. Now, permit me to just stop here for now, 8s. So I'm going to be filling all these guys maximally. You know the number of electrons as you go into S. From your, you know that S can only hold 2 electrons. P can hold maximally 6 electrons. You know, D can hold 10 electrons, and F can hold 14 electrons. So let me fill all of these now, and we add them together. So for everywhere we see S, you have a 2. For everywhere you see P, you have a 6 for everywhere. So you can get your calculator, and I want us to do this together actually. So let's see how many S do we have here all together. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 S all together. So that will be 8 times 2. I think I did not miss anyone out. Let's see how many P we have. 1, 2, 3, 4, 5, 6. 6 P's. So that will be plus 6 times 6. And let's see how many F we have all together here. I think we are done with everything here. Sorry, D is the next guy. 1, 2, 3, 4. We have 4 D's all together. 4 D's all together. So that will be 4 times 10. Then plus, let's see how many F's we have all together. I think F started around here. That's 1, 2. Only 2 of them. So that's 14 times 2. Yeah, or 2 times 14. Now let's do this math and let's find all of them all together. 8 times 2 is 16. 6 times 6 is 36. 4 times 10 is 40. 14 times 2 is 28. So let's add all these guys together. So we have 16 plus 36 plus 40 plus 28. That is 120. So you can see that from this diagonal, when I get to 8s, which is not even necessary here because 8s will carry 2, the maximum number of electrons that we can have is 118 as far as the periodic table as of today, number of elements that has been discovered is concerned. The maximum we have is 118. So the 8s is not needed. That implies that the last diagonal should be this. So everything from this place, so I'll just read it out with black. Everything from this place is not needed. And that is why if you notice in your off-bus principle, they are always stopping at 4F. And even though 5S, the energy level 5, is supposed to have 5 subshells, it goes only from 5S, 5B, 5D, and 5F. They don't go to 5G. That is not because it does not exist. Theoretically, it exists, but it is not needed. It is not necessary in filling anything up. Anyways, that's a lot of cumbersome thing to explain. Now, let's go back to our periodic table. So, I've told you that to know the block that something belongs to, all you have to do is to find the electronic configuration. You don't need to see the periodic table. So let me just pick 2 elements here. I will just use 2 elements to explain whatever I want to explain here. Let me pick this element here. That's 33. It has the atomic number is 33. And then let me pick somebody from, I don't want to pick, should I pick something? Let me pick this number 42. Number 42. So only those 2. So let's see how their electronic configuration would go. If we can get that, then we'll be able to get the periodic, the block that they belong to. So let's start. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we have 3d10. I'm just trying to exhaust as many as I can before I start dealing with the serious one. So 2 plus 2 is 4, 4 plus 6 is 10, 12, 16, 18. I hope I've not missed anything. I think I've missed something. 2 plus 2, 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 18 plus 2 is 20, 20 plus 10 is 30. So I have only 3 left. So after 3D, 4P is the next guy. So 4P3 like that. That's the electron configuration of this guy. Now, I think I should just copy and paste this. Control C. So we have 42 for this guy. So that means that 6 can actually go here. So 6 will go here. 4P6. After 4P, the next is S That's 5s2. And the next is 4d. The next is 4d. So let's see. I think from here we have 30. From here we have 36. 36 plus 2, that's 38. So out of 42, 42 minus 38, that should be 4. Yeah, that should be 4. That should be 4. So therefore we have 4d4. As you can see now, the last electrons fills the d subshell for this one. So therefore MO belongs to the d block. The last electron here fills the p subshell. Therefore this guy belongs to the p block. And as you can see, I picked AS from the p block that I've already identified earlier, and I picked MO from the d block that I've already identified earlier. So this is how you categorize elements into different blocks in the periodic table. Now that we are done with identifying the blocks that element belongs to in the periodic table, let's take a look at how can we identify the group that an element belongs to using the electronic configuration. Now, I know the general idea is that whatever the number of electrons are in the valence shell, that is the number of valence electrons, will always correspond to the group that element belongs to. However, this is not technically true. For the S block and the P block elements, we can use the number of valence electrons to determine the group that they belong to. But for the D block, that will not work. And F block, they are special elements. We don't necessarily categorize them under a group like that. We just call them the F block guys. So our focus will only be on S block, P block, and the D block element. So for the S block, it is quite straightforward. If you want to know the group that an element belongs to, as long as it belongs to the S block, just look at the number of electrons on it. So on the S subshell, the last S subshell that it has, just look at the number of electrons there. So if it is 1, it belongs to group 1. If it is 2, it belongs to group 2. On the P block, however, look at the number of electrons in the valence shell. Then you need to add 10. So for group 13, they will always have 3 electrons in their valence shell. For group 14, they will always have 4 electrons in their valence shell. The same thing for group 15. So all you need to do is that if it's a P block guy, look for the number of electrons in the valence shell and add 10 to it. However, for D block, these guys, they always involve the immediate S block. Now, for example, the example I did earlier. So if you look at this guy now, this guy, the immediate S block, has 2 electrons here and followed by the D block. So they always involve the S block and the D block. Normally, if you want to go by finding the number of valence electron, how do we even know the number of valence electron? Valence electron belongs to the valence shell, and valence shell is the outermost shell, that is the highest energy level in that particular atom. This energy level, like I've said earlier, they are represented by these numbers: level 1, level 2, level 3, level 4, and it goes like that. So whenever you see the electronic configuration of any element, like this one now, this AS guy, you can tell that the highest energy level occupied is the level 4. The highest energy level occupied is what? Level 4. So therefore, you can know the number of electrons in its valence shell. How many electrons do we have here for this 4s? We have 2. Plus, how many electrons do we have for this 4p? We have 3. So therefore, it has 5 electrons in its valence shell. And since it is a p block guy, therefore, you just add 10. So it belongs to group 15. Let's confirm that. So AS, yeah, it belongs to group 15. Now, for the S block guys, let me not talk about them since I have somebody from D block now. For the D block, what happened is that the highest energy level occupied is level 5. So therefore, the number of electrons they have in their valence shell is going to be 2. So it has only 2 valence electrons. But they always include their d orbital as well. They always include, their d subshell. So the immediate d subshell that even determines that they belong to the d block, you have to add that electron there. So this is 2, this will be plus 4, and therefore that implies that this element belongs to group 6. For them, you don't need to add any additional 10. Now, so I've explained for P block, I've explained for D block. Now, for S block, those ones are straightforward. So let's just pick a random element here. Let's just pick this guy, BA. That has 56. Oh my God, that's a lot. BA 56. Mm, I think what I will do is that I'll just copy everything here since it's better this way. So I know that this guy was 42 before. So 42, and I had 4 here. So if I remove 4 from 42, that would be 38. So this is 38. D can have 10. So 38 plus 10 is going to be 48. So 4D10. So that's 48 out of 56. That means that we only need 8 electrons left. Let me just move this up here so that I can rearrange it. Yeah. So we have 8 left. So after 4D, what's the next guy? After 4D, yeah, we have 5P and we have 6S. So let's fill that. So we have 5P6 and we have 6S2. So this is complete now. Everything here will be 56. You can just add the number of electrons all together. This is 10. This is another 10. So that makes 20. This makes 30. 30. This makes 40. 40. This is this with this with this. That is yeah, that makes 50 like that. So with this, then we have 56. Okay, so now you can see that this is an S block element and the highest energy level occupied is level 6. So therefore, how many electrons are there in level 6? 2. So automatically this guy belongs to group 2, and that is it. You can see I got that guy from group 2. So this is how you use electronic configuration to identify the group that an element belongs to. So for the S block, for the P block, and for the D block element. So please take note of this very well. And I hope you still have your notes with you. Make sure you take notes. I will take any question that you may have. Just drop it in the comment. I'll follow through everything. Now, let's talk about some trends that we follow in the periodic table. Also, there are some things about these valence electrons that I will explain in future topic. You can see, I think it's there in one of our days, where I will be explaining the VSEPR theorem, how they affect some things. So, but quickly, let's talk about the atomic radius. Atomic radius is simply the size of, we call it the size of an atom. So if you pick a specific atom now, the size of that atom, so we just use the radius to represent it. So as we have used from one shell to another, so we have, let's say, a particular element. So from the nucleus, it goes, it goes, it goes. So the atomic radius is simply from here to this place. So this, we just use it as a representative of the size of that atom. Now, as it goes from up to down, or they go from left to right, what exactly happened to this size? You should know that as it goes across the period, that is, as you go from left to right across the period, the atomic size will decrease. And what is the reason for this? It is because from the law of attraction, what happened is that unlike charges attract, while like charges, they do what? They repel. And as you move from, so I'm going to use um, this guy, beryllium and nitrogen. I'm going to use the two of them. So if you notice, both of them, beryllium is number 4 and nitrogen is number 7. So beryllium and nitrogen. So we have one shell here, the innermost shell. Let me make that a perfect circle. And then we have the outermost shell. Now for nitrogen, we have the innermost shell, we have the outermost shell. Anyways, the number of period also corresponds to the number of shell as well. So take note of that. You can see that already. Now, what is going to happen is that I'm going to fill, so this one, number 4. This one is number 4. And this one was number 7. So therefore, we also have 4 electrons for beryllium, and we have 7 electrons for nitrogen. So to fill the electrons now, from the rule I've given you already, you know that how many electrons will go here? 2. 2 can go in the first shell, and then the next shell can actually hold 8. So therefore, we can just pick a 2 and put it here. Now, this place we have 2 electrons here, and here we have 7. So that will be 5 left. So 1, 2, 3, 4, and what? And 5. So what happened here is that we also have 7 protons in the nucleus. Here we have 4 protons in the nucleus. Since unlike charges attract each other, here we have lesser number of proton and we have lesser number of electron. They are pulling on each other. But here we have more proton and we have more electron. They are pulling on each other. The thing is that the more they are, then the more the pull that they have on each other as well. So therefore, this guy will have a greater pull than this other guy. So if they have a greater pull than this other guy, that means that they will shrink this shell towards the nucleus. So the shell will be shrunk with greater force towards the nucleus than these ones will do. This one will have just a little bit of shrinking because the number of protons and electrons are not that much. So that is what happens as you go across the period. The atomic radius decreases due to that stronger attraction from the nucleus. Now, but as you go down the group, one thing you will notice is that as you go down the group, the number of shell will be increasing. So therefore, atomic size increases as you go down the group due to the increase in number of shell. The next one is ionization energy. What is ionization energy? It's simply the energy that is required to remove an electron. The energy required to what? To remove an electron. So how strong will you need to apply a force before you can remove an electron from an atom, especially from the valence shell? I think I should still use this guy from the whole across the period. So what would happen is that the energy to remove electron will increase. That is, ionization energy is going to increase. Why is it so? Reason is because, like I told you, the same reason. This one has lesser attraction from the nucleus. This one's out. There is a greater attraction from the nucleus. So if there's a greater attraction here, which one would require more energy to remove electron from it? Definitely this one, because there is a stronger pull. There's a stronger pull around here. Therefore, before you can collect electron from this one as well, you will need a greater energy. So that is why as you begin to go from left to right, there is what? There is increase in ionization energy. However, from as you go down, so I picked beryllium, so let me pick something under it. Let me pick calcium now. So if you pick calcium now, so you have, let's say, calcium, there's 20. So 1, 2, 3. Don't mind me, I'm just trying to be fast. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Then there's 1, 2, 3, 4. Anyways, what I'm trying to explain here is that as you go down, the ionization energy is going to actually decrease. Why? Because the proton that is in the nucleus, they are the one pulling the electron close to themselves. But if you notice this calcium now, notice that the electrons are getting far away. They are getting farther away from the nucleus. So therefore, the hold that the proton have on them, the hold that the proton has on them rather, is going to be decreasing. It's going to be decreasing. So therefore, it is going to be easier to remove electrons from this outermost shell than it is going to be from this one. These ones are closer to the out, so they are strongly pulled to themselves. So take note of that. That's for ionization energy. The next is electronegativity. What is electronegativity? I'm going to, like I said earlier, when I get to the VSEPR theorem, which I'll be talking about the shape of element and all of those things, I will explain this electronegativity better. So what happens is that in bonding, there is a place whereby elements they share electrons. They don't give or receive electrons, they share electron. Now it's possible that one side can pull electron to themselves more. One side can pull electron to themselves more. See, those guys that can pull electron to themselves more, we call them highly electronegative what element. So those highly electronegative negative elements, they pull electron to themselves more. Now, the electronegativity increases as you go across the period. At least you go from left to right, electronegativity increases. So that means that helium we have higher electronegativity than hydrogen. Neon we have higher electronegativity than lithium. However, um, when it comes to down the group, the electronegativity decreases down the group. It decreases down the group. I don't want to take too much of your time on this trend. We also have electron affinity. Electron affinity. It is the willingness to gain electron. So which one would likely gain more electron? As you go from left to right, it increases. Then as you go from up to down, it what? It decreases. That is, it decreases. It goes down. So that is for electron affinity. Then we have metallic character. Like I've explained from the beginning, you have guys with more metallic character on the left. So therefore, as you go down, as you go across the period from left to right, metallic character will decrease. And as you go from up to down, you have what? Increase in metallic character. One of the reasons is because as you go down, you see that there is more. When I was talking about that ability to lose electron, you remember that earlier. So calcium will readily lose electron. Yes, will readily lose electron than what? Beryllium, because there's a stronger pull between the proton and the electron of beryllium than that of what? The proton of calcium and the electron of calcium. So therefore, metallic character increases as you go down the group. So this basically summarizes everything on periodic table. It summarizes everything on the periodic table. So any other information that you need to know, I'm going to be giving you when we get to chemical bonding. And that's the end of today's class. Don't forget to share this with your friends, as many of your classmates as possible. That's one of the ways you can actually help me with the growth of this channel. Like, comment, and just engage with the video. I'll see you in the next one.